Hello, and welcome to Linear Algebra. This is lecture 22. Today's topic is triangularization. Last time, we talked about similar matrices. So these are the matrices that represent the same linear map, right? So you have a single linear map, but depending on your choice of coordinates, it has different matrix representations. This time, well, given that you have these different matrix representations, we can start asking for what is the best matrix associated to a given linear map. Okay, so in some sense, we won't get to the best answer today, but for some matrices we will. The simplest matrices, so what you might think is the best answer, are the diagonal matrices. Now, we've been talking about this, and if you have a linear map from the space to itself, then it is diagonalizable if and only if there is a basis of V consisting of eigenvectors of T. So we have a wonderful answer, in a sense, to when T is diagonalizable. Later, we'll see that for some matrices, this is automatic. Or for some linear maps, it's automatic. Let's state it for matrices. A matrix is diagonalizable if there is a basis of Fn. Consisting of eigenvectors of A. Okay, so there are matrices for which you cannot find an eigenbasis. So you cannot find a similar matrix that is diagonal. However, all is not lost. There are other matrices that are almost as good, essentially as good, as diagonal matrices. So in some ways, an upper triangular matrix is as simple as a diagonal matrix. Right, so here I mean simple in terms of understanding what the linear map does. So for example, if A is upper triangular, then, well, for example, one thing you can easily see if there are no zeros on the diagonal, then the matrix A is in row echelon form with a pivot in every column, right? And on the other hand, if there are zeros, on the diagonal, then the column containing the first 0 on the diagonal does not have a pivot. So we know that a matrix is invertible precisely when the reduced row echelon form is the identity matrix. So this tells us that whether or not an upper triangular matrix is invertible, we can just read off immediately from looking at the diagonal, right? That's excellent. And if we want to think about eigenvalues, well, we know that lambda is going to be an eigenvalue when A minus lambda times the identity is not invertible, right? But A minus lambda times the identity is going to also be an upper triangular matrix. And all we're doing is shifting the terms on diagonal by lambda. That means that we can find the eigenvalues very quickly. The eigenvalues of A are precisely the diagonal entries of A. Okay, so one necessary condition for a matrix to be similar to an upper triangular matrix is that it have eigenvalues, right? Because once you get to upper triangular, the elements on the diagonal are going to be eigenvalues. So this is a good time to point out that there are matrices that do not have any eigenvalues. So for example, say that you take the matrix A to be 2 by 2, 0, 1, minus 1, 0. Okay. So, and importantly, we're thinking of this as a matrix with real coefficients, right? So when we're looking for eigenvalues, we're looking for real numbers. Assume that you had some vector, say with entries A and B, so that when the matrix hits it, you get lambda times A, B. Okay. So writing out the product, we end up with two equations. Minus B should be lambda A, and A should be lambda B. And in particular, substituting the first equation into the second one, we have that A, I'll give myself more space. We have that A is equal to lambda B, but B is equal to minus lambda A. So this gives us minus lambda squared A. So putting the lambda squared on the other side, I end up with lambda squared plus 1 times A is equal to 0. Now, since lambda squared plus 1 is not equal to 0 for lambda in the real numbers, this implies A equal to 0. And then if you substitute that back into the equations, that gives you B is equal to 0. So there are no eigenvalues, right? The only vectors that are going to satisfy this are the 0 vector, and those don't count as eigenvectors. Okay, but it turns out that the problem here is the real numbers. So here's the definition. We're going to say that a field F is algebraically closed if every polynomial of degree n greater than 0. So for example, let's say you have p of x is a0 plus a1x plus dot 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 plus an x to the n, with a0 through an elements of the field and an not equal to 0, can be factored in the form p of x is equal to some constant times x minus c1 dot 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 x minus cn for some element of the field b c1 through cn in the field. Okay, so here the ci's, these are the roots of the polynomial. Obviously from the factorization, if you plug in x equal to cj for any j, this is equal to 0. Another way of stating this property is to say that every polynomial has a root, right? Because as soon as you have a root, then if you know that c1 is a root, then you know that x minus c1 divides this polynomial. And so then an easy induction tells you that p of x factors into this product of monomials. Okay, so a very important theorem that I'm sure you know, known as the fundamental theorem of algebra, says that the complex numbers make up an algebraically closed field. Okay, so over the complex numbers, every polynomial, we say, splits into a product of monomials. Okay, so the fundamental theorem of algebra is outside the scope of this course because it's not, well, it's not a theorem in linear algebra, really. It's not a theorem of algebra, really, because it requires more properties of the complex numbers than just their algebraic properties. But I'll tell you how you go about proving it. One way of proving it at the end of the lecture in the historical context section that you're free to skip. Okay, so, but it is important for the course that you know the fundamental theorem of algebra, because we will be using from now on that over the complex numbers, polynomials have roots. So in particular, here is the consequence you're expecting. If V is a vector space, of positive finite dimension, over an algebraically closed field, F, then every linear map from V to itself has an eigenvalue. Okay, so the only problem that can happen, the only reason a linear map would fail to have eigenvalues is because the field isn't big enough. It doesn't contain the solutions of the polynomial that came up. Okay, so let's do the proof. Let's let n be the dimension of the vector space, and so by assumption it's positive. So that means in particular that I can find a vector, say little v, that is different from the zero vector. now consider the list v, and then t of v, and then t squared of v, and so on, up to tn plus 1 of v, right? Actually, up to t to the tn of v. Now, when I write this, what I mean by t squared is just t composed with t, right? So this is, I take v, then I take t of v, then I take t of v, right? So I'm just applying t to the previous guy throughout. So this is just t composed with itself n times applied to the vector v. Now this list has n plus 1 vectors, right? In a vector space of dimension n. So it is linearly dependent. Okay, that means that there are coefficients a0 through an in the field, not all 0, such that if I take the linear combination a0 v plus a1 t of v plus dot 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 an tn of v, I get the 0 vector. Right? They're linearly dependent. That means there is some non-trivial linear combination equal to 0. Right? So pick one. Okay, now I know that not all of the coefficients are equal to 0, but of course some of them might be equal to 0. So let's suppose AK is the last coefficient not equal to 0. All right, so I'm just saying that AK plus J is equal to 0 for all J greater than 0. And let's let P of X, this is some polynomial, be A0 plus A1X plus dot 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 plus AN, no, up to K, AK X to the K. So this is a polynomial, the polynomial of degree K with these coefficients. Okay, so here there are no linear maps involved. This is just straight up the polynomial. I'm just taking the coefficients from over here. Okay, now since f is algebraically closed, we can factor p, right? So I can write p of x as b times x minus c1 up to x minus ck. For some b and c1 through ck in the field. Okay, so hence, I'm going to take the equation we had above, where we had 0 as a0, the vector 0 as a0v plus a1 t of v, and so on up to ak t to the k of v. And I'm going to say that that's the same as this factorization. T minus c1 times the identity, t minus c2 times the identity, and so on, up to t minus ck times the identity applied to the vector v. Okay, and the reason is just that that's the way the algebra works. This is this identity that this polynomial is equal to this one only uses facts about multiplication and addition in the field, right? And those facts, the distributivity of the multiplication among addition, hold just as well here when you're working with composition of the linear map. So let me do a quick aside. Just do an example. Let's say that p of x is equal to, let's say you were doing x minus 2 times x minus 3. So that would be the same as saying x squared minus 5x plus 6. Then let's say that you took t minus 2 times the identity, composed it with t minus 3 times the identity, and applied that to a vector b. Then what would this be? This would be, so t composed with t is t squared minus 3 times t minus 2 times t. So that's because the identity composed with t is just t. And then plus 6 times the identity, all of that applied to v, right? But of course, that's just t squared minus 5t plus 6 times the identity applied to the vector v, and that is t squared of v minus 5t of v plus 6 times v, right? So you see that the factorization of the polynomial means that when I have an expression like this involving the linear map t, it also factors into an expression like this involving the linear map t. Okay, but yeah, that's just an aside to justify what we did over here. Okay, so now let's stare at this. So let me rewrite it. Since b times t minus t1. Okay, so first let me note that b is not equal to 0, because if b were equal to 0, then this polynomial would be identically 0, and we know that it has degree k, so it's not identically 0. Okay, now since this composition applied to v is equal to the 0 vector, either t minus ck times the identity applied to v is equal to 0, or it's not. Or let's call it v prime, t minus ck, so the identity of v is not equal to 0. In the first case, v is an eigenvector of t with eigenvalue lambda. In the second case, v prime is a non-zero vector, and it satisfies b times t minus c1 times the identity dot 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 t minus ck minus 1 times the identity applied to v prime is equal to 0. So here, let me move this down. Okay, so either this last term gives us an eigenvector eigenvalue, or it doesn't. But if it doesn't, then that means that I have something very similar to what I started with, except that I now have k minus 1 factors instead of having k factors. So by a simple inductive argument, I'll just say continuing in this way, we eventually have a non-zero vector, say W, such that T minus Cj times the identity applied to W is equal to 0. Hence, right, because you keep going in this way, so there I remove the T minus Ck, and so now I end with T minus Ck minus 1. If I don't hit an eigenvector after K minus 1 steps, I'll eventually only be left with T minus C1 times the identity applied to a non-zero vector. And so I'll be in this situation where I now have an eigenvector and an eigenvalue. So at least one of the Cj is an eigenvalue of T. Right, and that's what we wanted to show. T has eigenvalues. Okay, so if we go back to our example, let's take the same matrix, but now let's think of it as a 2 by 2 matrix with complex coefficients. So we're looking for complex eigenvalues. Right? So let's do the algorithm from the proof. The algorithm from the proof said start with any non-zero vector. So let's start with, say, 1, 1. This is a non-zero vector. So in the proof, we noticed that no matter what vector you started with, if you take the vector and then apply the linear map to it enough times, you end up with a linearly dependent set. So this set is linearly dependent. Right, just because it has 3 vectors in a vector space of dimension 2. Right now, if we work out what these vectors are, that's the vector 1, 1. Hit that with A, you get minus 1, 1. Hit that with A again, and you get minus 1, minus 1. Right, and so yeah, that's linearly dependent. And indeed, if you take this one and you add that one, you get 0. So A squared V plus V is equal to 0. Okay, so this we now notice is the polynomial A squared plus the identity. So we should look at P of x squared plus 1. Right? Now, because we're working with the complex numbers, we're guaranteed that this will factor into a product of monomials. So in this case, x minus I times x plus I. Right? It's a difference of squares because in the complex numbers, minus 1 is a square. So coming back to our vector equation, I can write this as A minus I times the identity multiplying A plus I times the identity applied to the vector V, and we're guaranteed that that's 0. Now, from the proof, we know that either A plus I times the identity is equal to V, in which case V is an eigenvector with eigenvalue minus I, or A plus I times the identity V, call it V prime, is not 0 and a minus I times the identity applied to V prime is equal to 0. So that now V prime is an eigenvector and the eigenvalue is I. Okay, in this case, A plus I times the identity applied to V gives you minus 1 plus I, 1 plus I, and that's not equal to 0. So it must be that this vector, minus 1 plus I, 1 plus I, is an eigenvector of A with eigenvalue I. And indeed, if you do A times minus 1 plus I, 1 plus I, right, well, A just switches the, will give us minus 1 minus I here, and then minus 1 plus I. And you can easily check that that is I times minus 1 plus I, 1 plus I, as required. So there's the same argument, but in a specific case. Okay, wonderful. So now we have eigenvalues. We're guaranteed to have eigenvalues as long as we're working with an algebraically closed field. We're guaranteed to have eigenvalues. Now, as I mentioned at the beginning of the lecture, our goal is to start with a linear map and find a basis so that the associated matrix is upper triangular. So let's notice, just like we noticed that a diagonal matrix requires that the basis consists of eigenvectors, let's just think about what happens if you have a linear map and you pick a basis when is the associated matrix upper triangular? Okay, well, if it's upper triangular, then the first column is, only has a non-zero entry in the first entry, which means that when you're thinking about writing, right, remember the first column is the image of the first basis vector written using this basis. So that means that T of V1 has to be a multiple of V1. T of V2 gives us the second column. The second column, if we're going to be upper triangular, it can only have non-zero entries in the first two. That means that it has to only depend on the first two vectors in this basis. And so on. What we see is that T of Vj, right? So this would give us the jth column. The jth column can only have non-zero entries up to the jth entry. So we need for this to be in the span of V1 up to Vj. Okay, that's what it means for this associated matrix to be upper triangular. It means that when you look at the jth vector in that basis, its image is in the span of the first j vectors in that basis. Okay, now that we've noticed that, we can prove the theorem. If V is a finite dimensional vector space, over an algebraically closed field. And you have any linear map from that vector space to itself, then there is a basis of V such that the matrix associated to T in that basis is upper triangular. Okay, so this is great because, like we said at the beginning of class, representing a map with an upper triangular matrix is almost as good as representing it with a diagonal matrix. And this theorem says that as long as the vector space you're working with is finite dimensional over an algebraically closed field, then every linear map can be put into upper triangular form. Okay, so let's prove this. So let's let n be the dimension of the vector space. We will use induction over n. So for n equal to 0 or n equal to 1, there's nothing to prove. Right? If you have a one-dimensional vector space, then the map associated to T with respect to any basis is a 1-by-1 matrix, so it is upper triangular. So great. So that's the base case. Nothing to prove. Let us suppose then that the theorem is known for all spaces of dimensions less than n. Okay, so we have vector space of dimension n, and we are assuming that we know the theorem for all vector spaces of dimension less than n. Okay, so then what we want to do, obviously, is reduce the theorem for spaces of dimension n to something involving a smaller dimensional vector space. And what we know is because we have an algebraically closed field, we know from the previous result that this map has an eigenvector. It has an eigenvalue, hence an eigenvector. Okay, so from the proposition, we know that there is a V not equal to 0, such that T of V is equal to lambda V for some lambda in the field. Okay, let's let U be the range of T minus lambda times the identity. Right, so that is T minus lambda I applied to V, to capital V. Okay, so let's notice that T restricts to a linear map from U to U, right? That is to say that if you start with a vector in U and you apply T to it, you end up with a vector in U, right? So why is that? Well, indeed, if you give me a vector little u in capital U, then I can write T of little u, right? Remember, this is something I want to show is in capital U. T of little u, I can write as T minus lambda times the identity applied to U plus lambda times the identity. applied to U. Now this is in U because U is the image of T minus lambda times the identity. And this is in U because we know that the range is a subspace. And so if U is a vector in capital U, then lambda times U is also a vector in capital U. And because it's a subspace, if you have two vectors that are both in capital U, their sum is in capital U. So that shows that T restricts to a linear map between U, capital U, and capital U. On the other hand, since lambda is an eigenvalue, of T, T minus lambda times the identity is not injective. Hence, for example, by the Rank-Nullity theorem, T minus lambda times the identity is not surjective either. And since it's not surjective, that tells us that the dimension of U, call it M, is strictly less than N, right? Because this map is not surjective. Okay, well now we're in good shape to use our inductive hypothesis. So we have T restricted to U is a linear map from U to itself, and the dimension of U is less than N. Our inductive hypothesis says that we can find a basis, call it B sub U, so little u1 up through little um, such that T of little uj is contained in the span of little u1 through little uj for all j, right? Because as we saw, that's what you need from a basis in order for the associated matrix to be upper triangular. Okay, so now extend BU to a basis capital B, say U1 through Uj, and then the vectors we're adding will be V1 through Vk. And this is now a basis of all of V. Okay. So now I claim that this basis works, meaning that the matrix associated to T with respect to this basis is upper triangular. So let's check that. Note that. Okay, so what do I need to check? Well, I need to check this property, but now for this basis. I need to check that when you apply the ELF1 of these, the image is contained in the span of the first L of them. Right? Now, I already know that that's true for the U's, so I only need to check for the V's. So note that for any J in 1 through K, T of Vj, so here's what we'll do. We'll write that as T minus lambda times the identity applied to Vj plus lambda times the identity applied to Vj, just like we did a moment ago. Now what I know is that this term is in U, right? This lambda is the same lambda as above, so I get something inside U. And then this one, it's not in U, but it is a multiple of Vj. So I know that this is inside the span of, well, to get all of U, I just need U1 through Uj. And then I just need to throw in the vector Vj. I'm sorry, this should be a M. And then I just need to throw in the vector Vj. And since that is definitely contained in the span, if you now allow yourself all of the vectors V1 through Vj, then we're done. Then we know that the matrix associated to T with respect to this basis is upper triangular. Okay. Here's a simple corollary, just from knowing that you can triangularize a linear map. Let's say that F is algebraically closed. And P is a polynomial. With coefficients in F. Then the eigenvalues of P of A are of the form P of lambda where lambda is an eigenvalue of A. Okay, now notice that this is pretty awesome, right? Because if you had a matrix, say even a 2x2 matrix, then the powers A to the K are going to be pretty complicated, right? Pretty complicated expressions in terms of the entries that you started with. But if your matrix, let's say, was B, let's say it's upper triangular, then B to the K, well, this term is just going to be A to the K. This term is just going to be C to the K, and who knows what that one is, right? That's going to be something more complicated. I mean, we could work it out, but it's going to be something more complicated. Now, this matrix B, I know exactly what its eigenvalues are. Its eigenvalues are A and C. So the eigenvalues of B to the K are easy. They're A to the K and C to the K, right? So, but now the theorem tells us that every matrix of this form, as long as we're working with, say, the complex numbers, every matrix of this form is similar to a matrix of this form. So when I want to know what are the eigenvalues of A to the K, I can, by similarity, work with an upper triangular matrix, and then it's easy to see what the eigenvalues of B to the K are. They are just the kth powers of the eigenvalues of B, right? And of course, this was just a power, but if you take a polynomial, the same thing's going to happen. If you take a polynomial for a matrix like this, you're going to get very complicated entries. But if you take a polynomial of a matrix like this, some of the entries are going to be very complicated, but the entries on the diagonal are just going to be that same polynomial applied to the entries on the diagonal over here. Okay, very good. So that's the end of the lecture. Feel free to stop listening now. We'll have a short section on historical context where I want to give you a proof of the fundamental theorem of algebra. Okay. So like I said earlier, the fundamental theorem of algebra, despite the name, is not really a theorem in algebra. You can't give a purely algebraic proof because it requires some properties of the complex numbers that are not algebraic, right? Algebraically, you have this wonderful field, but the real numbers are a very nice field as well. And the real numbers don't have a fundamental theorem of algebra, right? There are polynomials with real coefficients that don't have real roots. So you need something that distinguishes the complex numbers. And so it really requires a bit of analysis. Now, it doesn't require much analysis. So we'll need, let's say, we'll use that a polynomial restricted to a closed and bounded subset of the complex plane achieves its minimum. Okay, so that's an analytic fact. And from this analytic fact, we'll be able to show the fundamental theorem of algebra. So here's the theorem we want to prove. So let's let P of Z be A0 plus A1Z plus ... up to ANC to the N be a complex polynomial of degree n, right? So by that, I'm saying that the coefficient A sub n is not 0. Then P has a complex root, right? That is, there is a complex number Z so that when you plug it in, you get 0. Okay, so I'll present a pretty simple proof. The idea of the proof is pretty old. It goes back to the beginning of the 19th century, but the version of it I'll present is a version of Charles Pfefferman. So we want to do this in 2 steps. First, we want to show that P of Z, the modulus of P of Z. Sorry, I should have said this context, this fact, the minimum modulus. Okay, so you take the modulus of this polynomial. So you're working with real numbers and you can talk about having a minimum. This obtains a minimum somewhere in the complex plane. Notice that this isn't just the statement I made up here, because the complex plane is not a closed and bounded subset of the complex plane. And then second, that minimum is 0. Okay, so those are the 2 steps. So for the first step, the main idea is that for C large in absolute value, the Z to the N dominates the other powers. Of Z, right? So this polynomial, you have a bunch of coefficients, but if Z is really large, then this c to the n is so large that I really don't care what the other coefficients are doing. This polynomial is really behaving just like a n z to the n. Okay, so let's write this like this. Let's just notice that I can write the modulus of p of z as I'm going to pull out mod c to the n. And so that's going to leave me with an plus an minus 1 divided by z plus dot 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 a until I have a 0 divided by c to the n. This is true for all z different from 0. And staring at that, we see that we can find some capital M such that p of z in modulus is larger than or equal to, say, a naught, or any number we like, but let's say a naught for modulus of c greater than or equal to m. Right. So if mod c is large, then all of these terms are small. And so another way of saying this, for mod c large, this is going to infinity. Right, but it's going to infinity in all directions on the complex plane. So I can find some mod m so that this is true. Okay, now here's where we're using the analytic fact. On the set of complex numbers such that mod c is less than or equal to m, the polynomial p of c obtains its modulus obtains a minimum value. So let's suppose that the modulus p of c naught, some point modulus c naught, is less than or equal to the modulus of p of z for all z less than or equal to m. Okay, now in particular, p of c naught is less than or equal to whatever the modulus of p of 0 is, right? Because that's 0 is a particular point with modulus less than m. And that is the modulus of a naught. I notice that sometimes I say modulus, sometimes I use absolute value. That's standard. After a while, you start calling the complex modulus just the absolute value of a complex number. So know that if I say absolute value, I mean the complex modulus. So in particular, this minimum, whatever it is smaller than or equal to the modulus of a naught, right? And since we've arranged for p of c to be greater than or equal to this for all z large, and now it's and we know that on this disk, the smallest you get is something smaller than a naught. We see that p of c naught is actually less than or equal to the modulus of p of z for all z in the complex plane. So this minimum, whatever it is a global minimum. Right? So, and we know that because it is the minimum for these values by construction, and its value is small enough that it's smaller than all of the values that modulus p of z can obtain for z large. Okay, so that finishes the first step for all C and D complex. That finishes the first step. Now for the second step, let's center things so that we can replace C naught with the origin, just for convenience. So to do that, let's write things like this. So since I can write P of Z as P of C minus C naught plus C naught, we can write P of Z as a sum of powers of C minus C naught. So for some complex polynomial Q, we have that P of Z is equal to Q of C minus C naught. Okay, so now let's rephrase what we've proven in terms of Q. We've shown that the modulus of Q of 0 is less than or equal to the modulus of Q of Z for all C in the complex numbers, right? And that's of course because if you write so Q of 0 is the same as P of Z naught, right? So this is just the same statement we had for P. I've just translated it into a statement for Q. Now we want to show Q of 0 is equal to 0, which will imply P of Z naught is equal to 0. Okay, so we've translated things to Q, and we just want to show that Q of 0 is equal to 0. Now, in the first step, we were looking at mod C very large, and so the higher the power of Z that you take, the larger the number you get. Next, we want to look at things that are close to 0, and here it's the opposite. As soon as mod Z is less than 1, taking larger and larger powers of Z gets you smaller and smaller numbers, right? So now we want to look at the smallest power of Z. That's going to be the leading term near 0. So let's let J be the smallest exponent for which C to the J, the smallest positive exponent, for which C to the J has a non-zero coefficient in Q. So then we can write Q of C as C0 plus Cj, C to the J, plus ... until you get to Cn, C to the N, right, with Cj not equal to 0. Also, Cn is not equal to 0. Factoring a Cj plus 1 from the higher terms, in this expression, we have Q of Z is equal to C0 plus Cj times C to the J plus C to the J plus 1 times R of Z. So for some complex polynomial, R of Z. Okay, So, and again, the point is that for z near 0, when I want to understand what this is doing, this is the leading term, right? This is the larger term, and for z small enough, this term is large enough that it swamps this guy. Okay, and now what's the strategy? Well, we want to show that q of 0 is equal to 0. Q of 0 is equal to z0. And we know that q of 0 is the global minimum for the modulus of q. So if c0 is not 0, we're going to show that we can find some point close to 0 where the modulus of q of z is smaller than the modulus of z0. And that will contradict this fact, right? And so, I don't know what r is, so I can't necessarily, I'd have a hard time finding explicitly a point where any particular value is taken. However, because for small mod z, this is the leading term, I'll just focus on this guy to make this small. And since this guy will be larger than this, that'll be enough. Okay, so that's the plan. Here are the details. Okay, let's set minus C0 divided by Cj to be okay, well, I'm going to write it in polar coordinates in the complex numbers, which means I can write it like this: r di theta and C1 equal to r to the 1 over j e to the I theta divided by j. So C1 raised to the j is equal to minus C0 over Cj. Okay, now if you've seen polar coordinates in complex numbers, then you know exactly what I'm doing. If you haven't seen polar coordinates used in the complex numbers, then just accept that I can find a Z1, some complex number, so that when you raise it to the jth power, you get this complex number. Okay, so in the complex numbers, you know that I can take square roots. Well, I can take jth roots as well. And this is just one particular jth root of this complex number. Okay. Right, and let me rewrite that identity as Cj times C1 to the j is equal to minus C0. Right, so you see that if I didn't have this term, then if I plugged in Z1, this would vanish. Okay, so now let epsilon positive be arbitrary. Q of epsilon times Z1 is equal to C0 plus Cj epsilon to the j, C1 to the j, plus epsilon to the j plus 1, C1 to the j plus 1, R of epsilon C1. Okay, now since polynomials are bounded on finite disks, we can find some positive number so large that this last term, R evaluated on epsilon C1, is bounded in modulus by n for all epsilon in the unit interval. Okay, using that, here we go. We take Q of epsilon C1, and we're going to bound this by, well, keeping the first two terms. So epsilon to the j, C1 to the j plus 1. And then the other term. So in absolute value, I can, in modulus, I can bound that. I can bound this polynomial by the sum of these two terms. And then, okay, so here, what I'll do is I'll pull out the epsilon to the j and just look at Cj, C1 to, oh, sorry, this is j plus 1, it's just j. C1, C to the j. And then here I can replace this polynomial with just capital N. Now I can rewrite this as, so Cj times C1 to the j is minus C naught. And this will be unchanged. And then notice here, I can write this as 1 minus epsilon to the j. That's a positive real number, so I can pull it out of this modulus, and it's multiplying modulus of C naught, and plus epsilon to j plus 1, j plus 1, times capital N. And then I can write this as modulus of C naught minus epsilon to the j, modulus of C naught plus epsilon to j plus 1, C1, j plus 1, capital N. Okay, so now finally, let's see what happens if C naught is not equal to 0. Then we can take epsilon so small that epsilon to the j plus 1 mod C1 to the j plus 1 times n is less than epsilon to the j mod C naught. Right, so this term, I can make it smaller than this guy in absolute value because I have an extra power of epsilon. In that case, this expression for the modulus of Q of epsilon C1 shows that it's less than or equal to, right, 0 minus epsilon to j C0 plus epsilon to j plus 1 C1 j plus 1 n, but by this assumption that's less than, strictly less than, mod C0, which is equal to the modulus of Q of 0, which is a contradiction. Right, because we said that modulus of Q0 was less than or equal to the modulus of Q of z for all z. Okay, that's a contradiction. Thus, modulus of C0 has to be 0. So Q of 0, which is C0, is 0. And that's what we wanted to show. Okay, so there you go. There's a proof of the fundamental theorem of algebra. And again, that's just historical context. It's not part of the course, will not be on the exam or the homework. Okay, we'll stop there and pick it up from there next time.